service attacks. So we are going to pick up talking about denial of service attacks, and then we will talk about other attacks on the TCP/IP layer. Particularly looking at IP spoofing and fragmentation and some IP traceback issues. So just as a reminder, here is our picture of the internet. We have our local area network, which is going to be Ethernet or Wi-Fi 802.11. We then have the wide internet as a whole, which is pretty much mostly runs TCP/IP. For routing, it uses BGP, which is a routing protocol to sort of decide how your packets get from one side to the other, from Alice to Bob. And then we have DNS, which controls how do we translate names into IP addresses. And we will talk about routing, BGP and DNS another day. For now, we're going to focus on TCP/IP. So last time we finished by talking about denial of service attacks. And the basic idea with denial of service attack is that you as the attacker are going to send a whole lot of packets to some victim, and you're going to send enough packets that will overwhelm them and prevent them from serving valid customers. And so the simple way to do this is you just use your machine and you send a lot of packets. The problem is that that takes a lot of your resources, so it's somewhat expensive. And it's also somewhat easy to block because the victim can see if the packets are coming from one source. They can just filter out packets that come from you higher up in the network someplace. You know, maybe their ISP does it. Maybe it happens even further into the network. And then there's no denial of service anymore. So the trick, or the interesting part of denial of service, is how do you launch a denial of service attack that can't be stopped? So one of the things we looked at yesterday, or on Tuesday, was using fake IP addresses as your source address. So you just fill in a fake address. You can still send a lot of packets, but they all seem to come from different places. And so the victim can't just filter out all the packets because they come from lots of different places, you know, which are all could be legitimate clients, customers, or, you know, somebody trying to access the server, so it's much harder to filter. But we still have the problem that the work that we're doing, generating and sending packets, is about the same as the receiver does receiving a packet. And that means that we have to have a pretty powerful machine to send a lot of packets, particularly because many interesting websites have, you know, 10, 100,000 web servers. So we need some way to get a lot more work done. And so the idea here is we want some asymmetry. We want to have this idea that we can do a little tiny piece of work, and we can make the server do much more work than we're doing. So we do a bunch of small, easy things. The server does a bunch of big, expensive things, and those big, expensive things block legitimate customers. So then the question is, as the attacker, what are the kinds of things we can make a victim do? What are the things we can do here? So there's really sort of three resources that we can control remotely. One is network bandwidth, how much bandwidth they're using. So this is a case where we send, you know, the problem is here we actually have to send requests ourselves. So the packet that we send uses the same bandwidth on either side. If we can get someone else to send bigger packets, that will help us. So we'll look for ways that we can send small packets that sort of lead to big packets being sent to a victim. The other thing we can look at is memory. Can we make the server, the receiver, use a lot of memory so they run out of memory and can't accept new connections because memory is finite? And the final thing is CPU. That servers need to use their CPU to process packets. I mentioned before, if we can send packets that take a lot of CPU time, that can block legitimate work from happening on the CPU. So, the Smurf attack is sort of an example of a simple asymmetry where we're going to send a broadcast ping. So a broadcast ping is a ping that you send, and it's broadcast, so it goes to everybody, and then everybody who gets that will respond to the source address. So this is great because it's a way to send one packet and you get a whole lot of responses. Everybody receives that broadcast. Now the downside is that, you know, broadcasts don't actually go very far. Broadcasts are pretty dangerous, so they're pretty heavily scoped. But it means that if I want to attack your web server, I can do an ICMP ping packet that I broadcast. I put your address as the source address. Everybody who gets that broadcast ping packet will respond, and they'll all respond to you. So I have sent one packet, and it's now been amplified by everybody who responded to send you maybe 1,000 times more traffic. So this is the kind of asymmetry that we like. This is an old attack, and you know, at this point, it's pretty easy to turn off by saying we don't really need broadcast ICMP messages anymore. Is this idea fairly clear? Oops, sorry. So here is sort of a graphical illustration of what's happening. Okay, so another thing we can do is we can think about what are the services out there that we can send messages to that will respond to us. And particularly what we want are services where we can send a single packet and they will respond with a bigger packet. If we have to create a TCP connection, as we'll see, that takes resources on our side because we have to remember the state, wait for packets to come back, send more packets. We want services where you send one small packet and the receiver sends one big packet or multiple big packets. An easy choice for this is DNS. So this is the domain name lookup system. When you use it, you send an address, you send the domain name like www.google.com, and then the server will respond with a list of saying, here's a whole bunch of addresses that correspond to www.google.com. And the nice thing is the response is bigger than the request, because the request just has the domain name you're looking for, the response has the domain name you're looking for, and a list of servers and maybe some other data. So this means that I can send a small, like a 65-byte packet to a DNS server. I forge the source address to be the server I want to attack, and the DNS server will now reflect this message and send a response back to the server. So I have now amplified the bandwidth that I can bring to bear on the server by a factor of 9 or so, by sending a bunch of these small DNS requests, and I can send them to all the thousands of DNS servers in the world, and they will all send their responses to the one server I'm trying to target. So this means that the server's getting packets from lots of different places. Each individual DNS server doesn't see that many unusual requests because I'm sending them to a lot of different places. And so it's very hard to sort of see that this is going on. So another thing you can do is if you can crash the server, that is sort of very asymmetric, right? If you can send one packet and exploit a bug in the server, then that will do a lot of damage on the server because they have to use all the time in CPU to reboot that machine. So for a long time, there was a bug in many implementations of the ICMP protocol used by ping. And so the ping protocol is intentionally, it says that the packet should never be bigger than about 8 kilobytes or so. But the format of the packet allows you to send a much bigger packet. You're not supposed to, but there's nothing that stops you from doing it. And so with the ping of death attack, you create a packet that is that is about 64K, and the server is expecting packets that are only 8K, and a lot of code didn't check to see if the size was bigger than 8K. It didn't handle it properly. So when it received this large packet, you could overwrite kernel data structures, which would crash the server or allow you to do stack overflows and remote code exploits and things like this. So the key here is looking for, the reason this works is people are able to find bugs in implementations of protocols where there are error conditions that shouldn't happen, that well-written code never exploit, so as a result, people never tested those error cases to see. So as an attacker, you try to look for, if you send a packet too big, if you sort of don't do the expected things, does it break the servers because nobody ever tried that before? So most of these attacks I'm talking about, there have been ways to fix this. This is just a bug in the code, right? This is not rocket science to fix it. You just have to check and do the right thing. But it's the kind of thing where this code is on, a million machines, and updating all million machines is hard. And it means that, every system out there was vulnerable for a while and could be crashed at will by anybody who wanted to. Are there other things you could do? Yes, Dolly.
So for the DNS protection that the way it is not possible today is because the spoof IP address packets have to.
Right, so we will get to a minute on how a bunch of these attacks are stopped. But you're right that spoofing IP addresses, source IP addresses, is much harder now than it used to be. Yes. So there are other things we could do, in advance of actually repairing the code on all our machines, and that's a problem because there might be things like you might have your X-ray machine running Windows 2000 that is on a network. And it's running a very old piece of code because it's a very expensive X-ray machine and not expected to be updated, and it's vulnerable to this bug. So are there other things you could do to mitigate this vulnerability? separately from actually fixing the code.
Not allow ICMP to outside the network.
Right, so there's certainly, the next step up is really to filter the packets. And in this case, you can either block ICMP altogether, and there's a lot of networks that just don't allow ICMP from other places. You don't really, there's no reason necessarily to allow ICMP. The other thing you can do is you can say, let's look for the packets that trigger this. If we know that the problem is an ICMP packet with a really big length field, let's just filter any packets that have a really big length field out, because we know that they're all taking advantage of this vulnerability. So that is a general mechanism that says if there's some particular bug where there's an unusual set of packets, let's see if we can detect those unusual packets at a firewall or some other switch in the network before they reach the server that's actually vulnerable. And this means you can sort of fix it in one place, and your servers, the servers can attack each other because they might not go through that firewall, but people outside your network can't do this attack anymore. Questions? Okay, so there's another class of attack based on IP fragmenting. So normally when you send data, it's going to be split into packets. And every network says how big packets can be. So for Ethernet, I think it's something like 1536 bytes. I'm sure someone probably in here knows the right answer, but it's on the order of 1500 bytes. So there's a question, what happens if on my network 1500 bytes is fine? So I generate a 1500 byte packet, but then it's going over to your network, and your network only allows 1024 byte packets. What happens to this packet? So one thing we can do is we can just drop the packet. The problem is we then need a mechanism to sort of tell the sender that the packet was too small and get the sender to resend everything. What happens instead is that this packet can be fragmented into two packets using this fragmentation feature. So an IP packet can be, I believe, up to 64K, because on some networks you might want big packets for efficiency, but then they can be fragmented into smaller packets when they're sent, when they get to a network that can't handle that. So this is controlled by sort of bits in the IP header. Here's sort of what the IP header looks like. And in this, there is some fragmentation information in the middle, these 3-bit flags and the offset. These flags tell you, is this part of a fragmented IP packet? And is it like the first packet, the middle packet, the last packet? And if it's a fragment, how far into the packet does this fragment come? So the question is, do you see any problems with this? Ben?
So this can cause the big that because you're allowed to send packets to starter and use those.
Okay, so one thing, if you have problems where you don't expect large packets, this can lead to large packets. So again, things like ping or death, any place you have code where it said really IP packets are never bigger than Ethernet packets, I'm not going to handle that case, this can lead to a problem. So that's one thing that can happen, is people just don't expect large packets to happen because normally they don't. Other things that might happen. Yes?
You keep saying it's more fragments, but store it back to memory.
Right, so another problem is, think about what happens when you receive a fragment. You were supposed to actually, in the networking code, wait until you get all the fragments and then reassemble the entire IPv4 packet and send that entire packet up to the next level in the stack, like TCP or UDP. So what this means is that you are allocating memory to hold a bunch of data, and you have to keep that memory allocated while you wait for the rest of the packet to come in for some time period. So I can now send you a packet and say, this is part of a big packet that's going to come in. This is the first fragment. It can just be a single byte that I send, but it's going to be part of a 64K packet. You allocate 64K to receive the rest of this message, and then I never send that message, and you're stuck there with 64K allocated on my behalf. So this is one way to sort of confuse, to sort of make the server use extra memory with doing very little work on my part by telling it to hold on to these fragments. Because normally when a packet comes in, the whole packet comes in, it processes very quickly, it gets sent off to the application handles it, it responds, and the whole thing happens in a millisecond. Here we can keep memory allocated for a second or something like that, a much longer period. So this is a way to sort of deny resources on the server. So ping of death is one example of this. The other thing is that the same thing that caused the ping of death, sort of faulty code, can happen with fragmentation. So fragmentation is something, as I've said, doesn't happen, never really happens in normal networks. And so the code to reassemble fragments wasn't very well tested. So you can imagine, like, if you send fragments that overlap, which should never happen, that code might break. And so it turns out, indeed, the implementation of fragmentation was broken. And in the teardrop attack, you could sort of send malformed fragmented packets that would cause the server to fail. This is when you have overlapping data. So again, the message here is, you know, if you wanted to look at a protocol, figure out the things that are legal but nobody does. Think about things that are allowed, for example, you know, reusing fields, overlapping information that shouldn't be overlapped, and sort of see, does the server handle that correctly, or do the designers, you know, were they grad students who just got it working and then the code sort of evolved for 30 years without being fixed because it never happened until you, the lucky attacker, finds the problem. So another thing you can do with this is you can avoid firewalls. So a firewall will typically take a packet, scan that packet, and say, does it look like a bad packet? Like, does this packet look like a ping of death packet? Well, what if you fragment your packet so you take that attack packet and you split it into two packets? So half the attack is in one packet, half of it is in another packet. The firewall almost never will sit there, hold on to packets to reassemble fragmented packets. They will look at the fragment and say, this fragment looks fine, and send it along. Because they don't have the memory to kind of keep this information around. They don't want to have the same problem of running out of memory allocating things. So by fragmenting your attack packets, you can then evade firewalls. So for example, suppose you are trying to launch a remote shellcode attack, one of these buffer overflows on a web server. That is normally or a SQL injection attack. Those are things that a smart firewall could detect by sort of looking at the packet and saying, oh, I see a SQL command in this HTTP request. If instead you fragment that command in a place so that whatever they're looking for is split into two fragments, then the firewall intrusion detection system won't see that it is in fact a code injection attack and will let the packets go through. So again, this is leveraging a couple of things. One, buggy code. It's leveraging the fact that for fragmentation, the rules that say you have to sort of reassemble things before you pass them along can make you allocate resources by making you use memory to hold on to it. Which means that either you can either make them use memory and run out of memory, or you can they won't do it, and then you can evade whatever scanning they're doing because they won't actually take the time to reassemble the full packet. Yes. So the ping of death is what I described before. This is where when you send a 65536 byte packet, it overflows the buffer that operating systems allocate to receive a ping message, and then crashes the system. So this again is just the format allows you to send a length this long. You're not supposed to, so operating systems didn't handle it, but they didn't have correct error checking to detect it. Okay, so the question came up earlier, which is, can these still be done? What do we do about it? So a lot of these one of the things that a lot of these attacks have in common, they don't all have in common, is that we're forging the source IP address. And what this means is if we want to track down the attacker and we want to, for example, arrest them or confiscate their computer, we don't know who actually sent the packet. So there's a question of how do you actually figure out who is attacking you so you can do something about it and arrest them. This is called IP traceback. And it means we're trying to figure out where packets came from, starting with the destination where the packet ends up and working back to the source, knowing that the source field is potentially wrong at all steps of the way. Any thoughts on how you might do this? It's not an easy problem, I don't expect it, but if people have interesting ideas, it'd be great to hear them. So it turns out I was office mates with one of the people who sort of developed a pretty cool technique to deal with this. There's a couple different ways of doing this. One way is logging. We're just going to have every router log the packets that go by for some short period of time. And so this means that if we want to see where a packet came from, we can go to our upstream router and say, we got this packet, where did it come from? The router looks at its log and say, oh, I got it from this other switch on my left, on port 2, go to that switch. You then go to that router and say, you know, I got this packet, it came through you, where did you get it? It can tell you where it got it. And if everybody across the network logs and keeps the logs long enough, you can basically work backwards to see where a packet came from. So this is nice. Do you see any problems with this approach?
At any point, a router could cease responding. Like an ISP.
Right, so the challenge is that it sort of gets, as soon as you have a single router that doesn't actually do this, it gets complicated. Because you don't know where the next hop is. Now, is that the end of the world? No, because you could potentially say, well, you only get data from 5 other routers. Let's go to all 5 of those routers and ask them. If any of them, if they all log, even though you didn't, you can just ask them what happened. So it's not the end, but you need a substantial number of routers on the internet and at ISPs to actually do this to figure it out. And so anything in the internet that requires global cooperation is almost impossible to pull off because, you know, these are multiple companies, they're multiple countries. You know, people don't agree, and they certainly don't move quickly even when they do agree. Another thing you could do is you could have every ISP could sort of allow filtering or do something when packets come in. So if every ISP allows you to sort of figure out where things are coming from, that can certainly help. So here we can do filtering. We can sort of control when packets come in, where they can go out of. This means that we can sort of say, we know that if a packet came in from here, it had to go out this other one. This lets us infer a little bit about what the routes are because we know that the rules only would allow it to take a subset of routes. So this makes it simpler so we can sort of know where the upstream switch was. But again, this is a distributed solution that requires cooperation. So what actually works in practice, but is not so good, is sort of to do a reverse DOS attack and to figure out who is harmed by that DOS attack. Let me just see if I have a slide. Okay. So what we're going to do here is we are going to flood all the output ports on our own switch individually. And we're going to see when we flood those output ports, which of those output ports is that we flood is the one that was causing the DOS traffic, right? So if we have 6 output ports and we flood each of them individually and the traffic is all coming from one, then when we flood 5 of them, the DOS traffic doesn't change. When we flood that 6th one, we see a change in the attack traffic. So that tells us that the attack was coming from that 6th port. So we're doing this by really trying to congest the resource the attacker is using and looking to see that the attack changes somehow. So once we know that output port, we now know the next router upstream. We can play the same game at that router. We send a bunch of traffic that goes in different directions. We can then see of the different directions which is the one that causes the traffic to slow down. And we can do this and work our way back until we get back to the original switch the attacker is coming from. Potentially, and sort of at that point, we sort of know at the point where you can actually, ask that ISP to filter traffic or to look at the traffic and see where it's coming from. So here we don't really need cooperation because we can on our own mount a flooding attack at all of these switches. Yes?
How is it like because we're still visiting the upstream routers?
Well, so when we say visiting them, we're just sending packets that go through those. So what you need to know is you need to know sort of the topology of the internet to know what are the different kinds of traffic I should send to this switch or this router to make it go in different directions. So it turns out there are maps that people build that will basically give you a map of all the routers in the internet that tell you how they're all connected together. And so we can use those maps to sort of figure out if we send this traffic, it will share the same link with our attack or it might share the link. But we don't need the owner of that router, the company running it, to do anything for us because we're just sending normal traffic over the internet. And we happen to be sending very targeted traffic that is trying to target a very particular switch. So we can also do this when we're doing our flooding. We can use 100 machines ourselves to do the flooding. We don't need to do it from one place. We can get all our friends at other companies to try to flood this one link and see what happens. Other questions on this approach? Yes?
This means that this is not real time when the attack is in progress. If the attack is done.
Right. In general, in all of these mechanisms, you have to do it in real time. Because the challenge is if you don't do it in real time, then you need to have records. And the problem is there's so much data going through the internet that you can't record every packet forever. And so even logging, it's just sort of a very short-term logging where you're logging a minute of data or something like that, which is still potentially, at every switch, there's gigabytes or terabytes of data at a switch or the router that are going through it. Yes?
If you had one server, like if you made one server, flood another server, and then it tried to flood that server back, and we're both trying to flood each other's links sort of problem?
It wouldn't actually be a problem. In some cases, it depends on how the network is built. A lot of times you have links that are bidirectional, and so you can send traffic in both directions without congesting each other. If you have a link where you're sharing the bandwidth in both directions, then you're right, that they would sort of congest that shared link, and you'd have problems. The other thing is that the directions you typically, when you send a packet in two directions, you very often take totally different set of switches. So if they're attacking you and you're directly attacking them, you might only share the links at the very end, but everything in the middle could be completely different. Other questions? Okay, so another approach is to say that, we can't record everything, but one of the things about a DOS attack is that there's a lot of packets. So if we mark a small fraction of packets with more information and we have a DOS attack, then with high probability, we will sort of get a lot of information. So suppose we say with some probability, every router packet goes through will append to that packet the address of that router, maybe 1 in 1,000 or 1 in 1,000,000 packets. So this means that the packets that you're getting in a DOS attack, maybe you get 1 billion packets. So what you do is you go through all those packets you're getting, and you look at all the routers, all the ones that are tagged with a router, and that lets you sort of build up a picture of all the routers the packets went through. And not every packet has all the routers, but enough packets have each of the routers that you get a complete picture. So this lets you, when there's a lot of traffic, if you get a single ping of death, it's not going to help you. But if you're getting a denial of service attack from a particular direction, this will let you know what that direction is without having to record a lot of information or do this reverse flooding. Now again, this works better if you actually have everybody participate, but to some extent what you really need to know is sort of who is at the origination of this. So if your edge networks are marking this, then that's sort of enough to figure out where the packets are coming from. So this is sort of a low overhead way of solving the problem. So you can also use ICP traceback. So this means that when you get a packet, routers can sort of periodically sort of probe where the packet was really coming from by sending an ICMP packet in the reverse direction when it gets a packet in to sort of probe where that packet was coming from. And this sort of builds up information again at the switch level on where packets come from. So this is sort of more intensive because you actually have to send packets out as compared to just marking packets that go through. So what do we really want to do about this? Well, we really want to do is to do filtering of packets so you can't fake your source address. So this can be done. There is an RFC for this, RFC 2827, and it's upstream ingress filtering. And the idea is that every network should only let packets into it that come from IP addresses that it thinks should be coming from that address. So this means that, for example, the University of Wisconsin has a bunch of addresses that it uses. There should be no packets leaving the University of Wisconsin going onto the internet with source IP addresses that don't belong to the University of Wisconsin. And so what the ISPs for the UW can do is to look at all the packets as they go by, filter those IP addresses and say, these are invalid packets and drop them. So if all ISPs do this, then there'll be no more source filter, there'll be no more spoofed addresses on the internet because every ISP will block those source addresses. You can also do this at higher levels in the network. It's a little harder because you don't know where the traffic is necessarily coming from. But you could potentially filter traffic at multiple levels. So here, there's a picture of it being applied in a backbone because it knows that it's getting traffic that routing tables sort of show should have a particular set of source IP addresses. So here is some up-to-date data. This is an organization in California called CADA. And they actually periodically probe the internet to sort of see what's happening. And what this shows is that if you look at IPv4 address blocks, these are sets of 256 IP addresses. 83% of those addresses are assigned to places that will do filtering on addresses. So these addresses can only come from legitimate places. The other addresses, 16%, are addresses that are spoofable, that they are not from places that do filtering. And so they potentially could come from multiple places. And so they're sort of untrustworthy. If you look at anonymous systems, who's actually, the different blobs in this picture, who is actually blocking things, we see that it's not quite as high. But, so the good news is that there's a lot of the internet that has ruled this out and is blocking addresses. And so this sort of source address spoofing problem is not nearly as big as it was a while ago. Okay, so if we can't fake our source addresses, this means that we need lots of legitimate source addresses. So how do we get source addresses? Well, we need to find other people's machines to send packets. So the old way we did this was a reflection attack, where we would send packets with a forged source address to someone else, that someone else would respond to us to the wrong source address and target our server. That's not going to work because we can't forge that source address. So now we're going to find compromised machines and ask them to send traffic. So this is sort of the idea of a botnet, that people can use the buffer overflows that you have implemented to take over people's machines, install long-running programs that can then be controlled from a central source. So people can build up large networks of machines that are compromised. They then have servers that are dedicated to controlling these machines. So you can go to one server and say, I want to have 10,000 machines that will all send this attack. They will then communicate to those 10,000 machines and say, send your attack to this set of IP addresses, and then 10,000 machines will send it. So the problem with this is that, it's very hard to filter because these are all legitimate machines that are all sending legitimate packets. The problem is that they're all sending them to one location, and the owner of the machine doesn't know about this. So here we can kind of see that we have lots of different compromised machines send it. So this was used, for example, to take out the internet in Estonia. Almost the whole country was shut down when supposedly sort of Russian organized people all sort of flooded Estonia with packets. And so, almost every major website in Estonia was hit at the same time, and the whole country sort of lost internet access through this attack. The other way this has been done is people figured out vulnerabilities in webcam software. So lots of people have webcams. There's tens of thousands of them. So if you find a vulnerability, you can then take your webcam, which is mostly running some version of Linux with a password that almost nobody configures, go to these things. They're certainly powerful enough to send packets like this. You can turn them into a very large botnet that attacks anybody you want to. So botnets are still sort of a large problem. Okay, so that was sort of the IP level problems, and we're now going to sort of move up to the TCP level. Any questions on IP and those level problems, Natalie?
So this also means that the spoofing is based on that your source address should be from the network is supposed to be.
Yeah.
That means you can spoof addresses from within the same network, in fact.
Yes. So I can potentially spoof your address, any of your addresses at the University of Wisconsin. So what can we do about that? How do we solve that problem? Thoughts?
Potentially introducing that.
Exactly. So these switches at Wisconsin, they know your MAC address, and they can say, given your MAC address, we will only allow IP packets with the IP address assigned to this MAC address. And so the switches at Wisconsin, I believe, generally will do filtering that way. They will make sure when you connect that you can only send packets with your source address. So the same kind of filtering can be applied locally within an organization. So the other thing to note is that, so what this means is that within an organization, you can actually totally prevent source address spoofing. So this means, for example, if you go to Amazon and run a machine in AWS, or go to Google and run code in Google Cloud, or Microsoft you run on the Azure Cloud, there is no source address spoofing on those networks. So when you get a packet with a source address, you can be guaranteed the packet actually came from that machine that had that source address. And so it's a sort of a different problem. The internet, the problem is you have all these independent entities that have to cooperate, and so nobody can sort of control everything and actually enforce these rules. Within an organization, though, you can definitely enforce all these things. Okay, so let's move on to TCP. TCP is the next level up in the stack. It is connection oriented. It's meant for sending a stream of data, not just a single packet. So you start this by doing a handshake, much like the handshake we saw with TLS, where we're going to sort of send messages back and forth to negotiate a little bit. Then we can send packets, and the packets are just sort of offsets in an infinite stream of bytes, so that every packet has some data with some range of offset, and then the receiver will reassemble all these packets to actually generate the stream of data at the receiver. It also provides reliability, meaning that if packets get dropped or damaged, they'll be resent. So to handle this, receivers, when they get a packet, periodically at least, they will send an acknowledgement saying, I got this packet. When the sender gets an acknowledgement, they know the packet has been delivered. I can drop the packet. If they don't get an acknowledgement, they might resend the packet after a timeout, so that in case the packet was dropped and not the acknowledgement, the packet gets out there. So there's basically a window on either side of packets. And what we're trying to do is to copy this window of packets over here. And once it's been acknowledged that the packet has been received, we can sort of forget about these packets and now start sending the next packets. So that's kind of the basis for TCP. So something this means is that packets can get reordered in the network. You might have packets that go through different routes in the network, different routes in the network that arrive at different time, in a different order than they were sent. So this means that receivers have to have buffering space to be able to reassemble things out of order. They might find that some of the packets are dropped in the middle, so they have to sort of be able to remember what was dropped and say, this was dropped, please resend it, and then reassemble things. And only when the data is actually reassembled does it get delivered to applications. The other thing we need to worry about is flow control, right? We have some buffer on the receiver to receive data. We need to worry that if the sender sends too fast, they might fill up this buffer before the receiver can process it. So like if I'm sending from a supercomputer to a cell phone, the supercomputer can output maybe a couple terabytes a second. Your cell phone can maybe receive a gigabit per second. So we need to make sure that it only sends at a speed where the receiver can handle it. So that's where flow control comes in, and basically it says that the sender can't send more data until the receiver has acknowledged that there is space for that data to exist. So this will aid the sender from sending while the receiver is processing data. The final thing we need to worry about is congestion control. So flow control really is about, can the receiver process data? What happens if you're going through a switch and everybody else is sending data at the same time and that switch backs up and starts dropping packets? What you want to do is have everybody slow down and send at a slower rate. So that is called congestion, and congestion control algorithms sort of get everybody in a distributed fashion to send at a slower rate so they don't drop packets anymore. So needless to say, this complexity is great for malicious people because there's lots of different pieces that you can abuse or that might be implemented the wrong way. So here's our beautiful picture of a TCP packet. You can sort of see it fits into an IP packet right after the IP header before the data. Here, what we've added are port numbers. So port number says sort of what application did it come from on the sender side. The destination port tells you more or less what application is it destined for. Is it for a web packet destined to a web server? Is it an SSH packet to an SSH server? We have a sequence number that says in the stream of data, where does it fit in the stream of data? There's an acknowledgement number, so we can say this is the data that we've received in return, so we're piggybacking those acknowledgements. We then have more information about a checksum and some other data about whether it's urgent, and information about the window size, or really how big is this window here? How much data can we have outstanding at a time? So we're going to do sort of a quick lightning tour of TCP and how it gets going. We have about 15 minutes, so we'll see how far we get. So this is called the TCP three-way handshake. This is how you start a connection. So the sender will send a SYN packet, and it will send a client sequence number to the server. The server will respond with its own SYN packet, and also putting an acknowledgement bit in here saying that it acknowledges receiving the SYN packet. It's going to send back its sequence number, and it's going to also send back the client sequence number incremented by 1. And then the client will send back its own another acknowledgement saying, yes, I received your packet, and it's going to send back the sequence numbers to the server. So after this, both sides have been acknowledged that the connection is established. The client was acknowledged with its, the server knows that it got its packet back. And we are sending back and forth the sequence numbers of the data that we're sending, as well as an acknowledgement number that says this is the data that we have received from you successfully. So we always send these back and forth because the client and the server can both be sending data to each other. So when you're done with the connection, one side can send a fin packet, which means we want to finish it. And you send the sequence numbers again that you want to finish here, and then the client or the other side will then acknowledge, yes, we're finished with this, and then both sides can delete whatever data structures represent this connection. So that is sort of the lifespan of a TCP connection. Okay, what can we do wrong? Well, the astute attacker should notice that when you send a SYN packet, the other side has to allocate memory and remember your sequence number, because they're going to be expected to use that sequence number in the future. So this is what we look for, an asymmetric attack, where I can send one packet and I can make you do more work than just receiving a packet, because I can send a packet and make you allocate memory. So in a SYN flood, what I do is I just send you millions and millions and billions of SYN packets that you allocate memory for until you run out of memory, or you spend so much time handling these packets and allocating memory that you can't handle legitimate customers or legitimate users because you're so busy handling my packets. And the rules say, there's some time window at which you're supposed to keep the SYN information, the sequence numbers around, because you might have a client connecting over a really slow link, and they might be connecting from Antarctica over a satellite, so it might be that each of their packets takes a second to get to you. So this means that when you get a packet, you're supposed to keep it around for a second or two to wait until you get the acknowledgement. So this means that you can allocate memory and keep it allocated for quite a while just by sending a SYN packet. The other thing you can do is, sorry, we're going to back up. Okay, so before we move on, what can we do to defend against something like this? Any thoughts? Yes?
If you see so many SYN packets, then stop processing.
Okay, so one thing we can do is we can basically, if we see too many SYN packets, we can just start dropping SYN packets and saying, we don't know, these clearly aren't real, they're interfering with us, we're just going to filter them. We might filter them with a firewall, we might have the operating system filter them in some way. The challenge with that, of course, is that legitimate users are also trying to connect with SYN packets, and so your normal users will still get blocked out, even if you're still able to function. Yes?
So if we see a lot of SYN packets from one IP, we will block this IP.
Right, so we can certainly, if it's not a distributed attack that's from a single source, we can certainly fairly easily block one source from sending a lot of IP address, a lot of SYN packets. Other things we can do. So again, took a lot of cleverness. Another way of doing this is to say, why does the receiver actually have to remember things? Is there a way that we can modify the protocol or use the protocol but modify the implementation so the receiver doesn't have to remember things? So remember, in the protocol, the server is supposed to remember the sequence number that it's using, the server sequence number, so it can use it again in the future when the connection actually happens. So the thing to note is that the client here is providing the sequence number, the server sequence number back again. So is there a way that we can say if the client's going to remember the server sequence number, seek S, why should the server remember it? And this is called a SYN cookie. And the idea here is that we're going to take some random sequence number, we're going to encrypt it, we're going to send it to the client and then forget about it. The client will then send us back the encrypted sequence number. The server can decrypt it. If it decrypts successfully, then it's a valid connection. If it doesn't decrypt successfully, we know it's a bogus packet. And so the key thing here is we don't have to allocate any memory to remember this. Instead, we make the server remember it, the client remember it, and send the packet back to us. At least until we have the connection established. Yeah.
Access storing the encryption key, right? Isn't that similar to storing the sequence number?
The thing is, you can use the same encryption key for everybody. So you can have one encryption key that you use for a million different clients. So that's where you get a benefit. If you had to have a different encryption key for every client, you would be absolutely right. So that is sort of one way of solving this, and it's a general approach of move the work from the server to the client by encrypting things, make the client store them, and then on the server just verifying things are correct through cryptography and MAX, instead of actually recording data. Okay, so another question is, suppose we have a network that allows source address spoofing. So far we talked about using source address spoofing with single packets. In a single packet it's easy because that one packet is not in the middle of a sequence. Anybody can send that one packet. What if I want to send a packet that is a valid TCP packet? So when I send data for TCP, every packet has a sequence number that says what is the byte offset into my stream of data that I'm trying to send. This means that as an attacker, you need to sort of predict, if you want to send a packet that comes from me, you actually need to figure out the sequence number. So think about, for example, if I want to do this handshake here, and I want to spoof the address, there's a problem that, I'm going to spoof the first packet with the server's going to respond, but the packet goes to somebody else, right? I can't see that response, so I can't send the third packet to actually complete source address spoofing, because I'm not going to see the response that tells me the server sequence number. So there's a question of what can we do about this? So one thing is it tells you, what happens if I could predict what these sequence numbers are? Like if I knew what the next server sequence number is, then I could send a SYN packet with your address, the server sends a response, I can then send the final ACK packet there with the sequence number the server was using, even though I've never seen it, because I can predict what it is, and I can now send data as you to that server. So this is why sequence numbers, having them be predictable, is not a great choice, because it allows you to actually sort of have a full communication with somebody back and forth. So it turns out, of course, that before people thought about this, this wasn't properly used. So two things that people used to do. One is there were a whole set of programs for Unix system called the R suite of utilities, RSH, RLogin. This is basically before SSH, and RSH and RSH would basically let you connect to remotely log into some machine and get a shell there, and all it did was look at your IP address. It said, if you come from this IP address, we're going to trust that you are who you say you are. So the security was totally based on the IP address being safe. Now it's a TCP connection, so if you can just spoof a single packet, you can't really actually log in and do anything. You have to spoof the whole connection. So if we can predict the sequence numbers, then we can actually spoof the whole connection and send all the packets in the connection using sequence numbers that we predicted. It turns out that Unix BSD 4.4 had a pretty bad way of producing sequence numbers. It would set the sequence number to 1 when you first initialize the system, and then it would sort of increment it for every additional connection that you made. So this means that if I'm the attacker and I connect to a server and I see the sequence number, and then I can see the current value for the sequence number it's using. If I then send a spoofed SYN packet, I know that it will be that same sequence number plus 1, because it just increments the initial sequence number by 1 every time. So this made it really easy to actually guess the initial sequence numbers. They later changed this to sort of increment the sequence number much more quickly by sort of 64,000 every half second. But it turns out that sending a lot of packets isn't that hard. And this means that it's not, you can't do it every time, but you can still guess sequence numbers. So what you really need to do is have some totally random way of generating initial sequence numbers that can't be guessed. This makes sense. So there's another flaw here, which is a bigger design flaw, which is that people were sort of assuming that TCP couldn't be spoofed when they built systems like RSH, where they just use IP addresses for security. And TCP, if you look at the design documentations, nowhere does it say this is a secure protocol. Nowhere does it say this cannot be spoofed. It just says we provide you a reliable connection. And the RSH people said, I don't know how to spoof this, so it's got to be secure. Let's make it really easy to log in. You don't have to type your password. This is great. Everybody hates typing passwords. We'll just use IP addresses. And so it was a flaw of TCP not being secure, but a bigger flaw of people thinking TCP was secure and building a system based around this falsehood. So the other thing you can do is you can be malicious and you can send a FIN packet. So in addition to sort of injecting packets, you can terminate connections. And it turns out that a FIN packet is even easier. For a FIN packet, the sequence number has to be anywhere in the congestion window, which is about 32K or 64K. And so this means that if you can guess, within 64,000 of the right sequence number, you can terminate a connection and you can sort of make people stop what they're doing. And so this is highly irritating and is sort of a fairly simple denial of service attack you can launch. So this is sort of an example of what you can do with forging. So as I said, the better fix is the random sequence number for every connection. So there's some other issues with TCP/IP. So we talked about congestion control. It turns out that congestion control is really up to the client to implement. You can modify your machine to implement any congestion control you want, and you can just send packets faster, and you will get better performance by doing that. And there's actually people where you can download TCP stacks that will ignore the globally agreed upon rules for congestion control and give you better performance by abusing the system. I don't recommend you do it, but it does give you better performance because every place there's congestion, you will get more packets through than anyone else. Early problems is there's no cryptography. There's still no cryptography. It's sort of been bandaged on top. And we'll talk more about routing problems and DNS problems. So needless to say, networking is a great source of security problems. We will pause here till after spring break and then pick this up. So one quick note is I'm going to be out of the country after spring break. And so I think one of the 2 days I will record a lecture and post it on YouTube. The other day we're going to have a guest lecture talking about privacy issues. And it's a grad student doing research in privacy, and she'll sort of teach you about how to actually make things really private. So what that means in a strong cryptographic sense in a way. Okay, so have a great spring break. Good luck finishing project homework 2.